Okay, so let us continue on our discussion on second module. So in that we were discussing about the discrete logarithm, and I told you that this will be useful, especially with the RSA algorithm, which is an asymmetric key algorithm. Will come at in the fourth module. But again, as we are discussing all the principles or the mathematical fundamentals which are required for the different algorithms, this is also part of that. So in discrete logarithm, what happens is that we are supposed to find out order of the element of a set. Order of the group, we already know that the number of elements will indicate the order of the group. But order of the element also will play an important role in this particular case. So let us first define that. So order of the group, as we all know, that it is the order of a finite group is capital G. It is represented usually by mod G like this. And it is the total number of elements in the group. Total number of elements in the group. So for any multiplicative group, or for that matter any other group, multiplicative group, naturally the number of elements will depend on the multiplicative inverse property. But other than that, for any other group also, whichever be the number of elements, that many number of elements will be the number of that will be the order of the group. But as you can observe over here, that if it is G7, the group is 7 Z21, and it is a multiplicative group with the operator multiplication over here, or cross if you consider the binary operator, then we are observing that this 21 will be divided into phi 3 and phi 7. Remember the process that is involved over here. This is with respect to the Euler's theorem, how we are doing it. And if you observe that the total number of elements or the order of the group in that case will be 12. Because it's a multiplicative group, because this star, if you remember, I told you that this always indicates that this is a multiplicative group. So 12 number of elements will be there, which will form the group. And naturally, you can see that these are the elements which, if you go on computing the GCD of it, you will find that these are the elements which actually forms the group. And there are total 12 such elements. So hence we can say that this group belongs to have 12 as the order. Now, in the same manner, order of the element, this is something new that we haven't discussed. Yeah. So order of the element usually is represented by odd of A. If you see if an element, if you consider, suppose it has 4 elements. Suppose we have, the example is here, but suppose you have 1, 3, 7 and 9. This forms the elements in a particular group, certain group. Then what will be the order of the individual elements? This is what we have to consider. And that calculation, so order of 1, order of 3, order of 7 and order of 9. That only element wise ordering is to be done using a certain formula. Alright, and that in fact is the basis of the discrete logarithm, and this is the formula given over here. Please make a note of it. Very similar to what we have discussed over the period of time. So it is given by a to the power I congruent of E mod of n, where E is the identity element. If you observe here, already we have established that. That is why the reason why we have discussed the properties of group and field and the communicative, associative, identity, inverse properties, all those things. So in this case also you can observe that this E will belong to, so for a given group, we can find out that what is the identity element, and given the identity element, we can find out what is the, or A, what is the value of this, for what value of I this equation holds. Alright. So you can see that order of A is the smallest integer I. So we have to find this I, smallest integer I, such that this equation holds true. Now how it is computed, you observe over here. Now we have taken an example of Z10 star, which means multiplicative group Z10 is what we have considered. So the base is 10. But if you remember, and if you can do it also now itself, that if you consider phi 2 multiplied by phi 5, if you consider this one, phi of 2 multiplied by phi 5, like this if you do it, and if you go on producing the number of elements, you will find that the element phi 10 will always be equal to 4. We did it actually. For Euler's theorem, we have already done this. So the elements what we have is 1, 3, 7, 9. Now if you observe that how this equation is formed. Now closely observe that we have following this equation. Alright. Where you have the A as 1, 3, 7 and 9. Now if you observe carefully, we will just go on trial and error method. We'll see a better example next slide. So what we are doing is 1 to the power 1. Now 1 as the first element is 1. So this element I'm talking about. So 1 to the power 1 and any other power, whatever we are considering, always this equation will hold true. So we can write that odd of 1 is 1. Understood? So what we are looking at is that the equation, because this E, why it is 1? Because if you observe or if you remember, I don't know whether you remember it or not, we actually had solved this long back, that this for Z10 star, or if it is a multiplicative group, the identity element will be 1 for all cases. Because it's very simple. You can see what was the property for multiplicative, for the identity element? A dot E equals to E dot A. That was the right. So if you observe that if you consider 1 dot dash is equal to dash dot 1, where this operator is multiplication. So it can only be either 1, other than that this equation doesn't hold. And for all the other elements, suppose 3 multiplied by something, which will make it something multiplied by 3. So it will always be 1. Other than that, this equation doesn't hold true. So basically, that's why you can observe that this E element is 1. So for each and every group, we have to find out what will be the identity element. Given the identity element, that identity element will be replaced over here. And accordingly, we will have to find a to the power value of I such that the minimum I for which the equation holds true. So for this particular example, E is equals to 1. For this example, identity element is 1. So we are trying to find out a way in which this equation holds. So you can see for 3, when we are looking at 3, 3 to the power 1 is 3. So 3 to the power 1 divided by 10, the equation doesn't hold true. 3 square, if you consider 3 square divided by 10, doesn't hold true. 3 cube, 3, 4 if you go, you see this equation is matching. So we can say order of this is 4 for this all 3, right? So the order of elements should be considered with respect to this particular equation, a to the power I congruent to E mod of n, where E is the identity element. For every group, we have to find out what is the identity element, and then we have to substitute and satisfy the equation to find out I. Now to make it a little more elaborate, this is 4 examples, only 4 elements which are present. So let's take a little bigger example. For example, this is where we are considering Z8, okay, which we haven't done as much. Alright, so Z8 is one of the factor. Now in that it's already, I have explained over here. So what we are looking at that using Euler's theorem also, we are integrating the same like we did in the previous case. So we can also mention in the same manner a to the power 5n. Instead of a to the power I, we are mentioning a to the power 5n. See the condition. Relationship AI congruent of E mod n holds when I is equal to 5n. Alright. So if the phi n is the value that you are getting from Euler's phi equation. If that is equal to I, then we can replace that by the equation on top over here. Okay, over here, and that is much easier equation for that matter, because if you observe over here, you don't need to bother much about the identity element at all, because you can see always this will be 1. Okay, so you can see over here what this table shows us. So what they have done is that for phi 8, for Z8 rather, we can calculate it accordingly. I will just give it over here so that we understand that why it is 4. So you can see 2 cube is the prime number. So if we have that, if you observe the fourth property, I think for phi Euler's theorem, we can divide that into 2 cube minus 2 square, and that will eventually give us the value of 4. And eventually what is happening, those 4 are being arranged over here, similar to the previous one. And on the x-axis, what we are plotting, if you observe that we have I equals to 4. Up to this point, you observe over here. Okay? So I equals to 1, 2, 3, 4. What is phi n? Phi n is 4. So we have now for these 4 elements, what we are observing, what is the specific value of I such that for the particular A, the equation holds. So if you observe over here, for 1, it is fine, all will be 1 anyway, leave out that. But in that also, you can observe that one specific block has been made a box. See this? We have made a box over here. So that is the minimum value of I for which for the element 1, the order is 1. So you can observe over here for this element AI, okay, this is for the A element. At I equals to 1, we are getting a 1 as a response. So we will say the order of 1 is equal to 1. Am I clear? Next one, if you observe, A equal to 3. Now we go on multiplying 3 to the power 1, 3 to the power square, like that we go on. But as the base is 8, if you observe that at this point, we are getting a 1. Remember in the previous case, Z10 was there. That's why the order of the element was coming as 4. But here the order we are getting as 2 and we don't need to worry about the identity itself. Listen. So what will be the order of 3? Order of the 3 will be confused. What we are trying to observe over here, we are trying to find out the value of I for which the equation holds true. In the previous example, we had to find out the identity element of the group. But over here, using the Euler's theorem, we are not going to use the identity element. We are just generic equations we are writing over here, where phi n will be varying till, or rather I will vary till phi n. So what we are observing over here, for I equals to all other elements, we are going on substituting the values of x. Like for what value of x it is actually matching. So you can observe over here the first element at I equals to 1 it is coming as 1. For 3, when I equals to 2 it is coming as 1. For 5, same. For 7, it's same. So the order of Z8 or the elements within Z8 as a multiplicative group will be like odd of 1 would be 1. Odd of 3 would be 2, odd of 5 will be equal to 2, and order of 7 would be equal to 2. Because this is the, see over here also we are getting x equal to 1 or remainder equal to 1. But as we have mentioned that I should be minimum, the smallest integer value for which it has come or it is satisfying the condition. So this is the minimum value of I for which the condition satisfied for 3, 5, 7. That's why we are considering the order as over here as 2. Any doubt over here? Anyone having any doubt over here? We'll see another example also next after this. But now observe carefully that even if I go on increasing 5, 6 and 7 different values of I, the whole pattern actually repeats. So we don't need to bother much after phi n. That is why the condition I phi n holds. Because this 5, 6, 7, this whole pattern has 3, 1, 3, 3, 1, 3, 5, 1, 5, 5, 1, 5. So it repeats again. So we don't need to worry much. So the advantage of from the previous equation to this is that we don't need to calculate the identity element for a particular group. Okay, so that is the less hurdle that Euler's theorem actually gives us. That's why we have done Euler's theorem prior to it, or Euler's phi equation for that matter. So keeping that in mind, so this is again the explanation of it, and you can see that it's already mentioned over there. Now let's see. This is wrong actually. This should be 2 actually. This should be 2. Anyway, this is the same thing. Now let's see about Zn. Now this holds important information over here. See the definition as I mentioned, that when the order of an element is the same as that of phi n, please make a note of this. When the order of an element, now we know about the order of the element. Each individual element will have an order, and that should be found out by a to the power phi n congruent of remainder, that is 1 mod of n. Now, when the order of the element is the same as that of phi n, then that element is called as the primitive root of the group. These are all required later on. Unfortunately, I cannot relate to that right now, but for the time being, please make a note of it. So order of the element, if it is same as that, like for a particular element, if the order is same as that of the phi n, then we will call that particular element as the primitive root. For example, if you observe over here, this is a group The same thing that I've taken, Z8. Okay? Now, if you observe here, for all the cases, what was the phi n over here? What was phi n? Phi 4. Like it was 4, it's coming as 4. The phi 8 is equal to 4, to be honest. So the phi n value is 4. Is there any order of a particular element which matches to be equal to 4? Is there any element like 1, 3, 5, 7 for all these 4 elements? What are the orders we are getting? 1, 2, 2, 2. So there are no such element which has an order which is same as that of 4. Hence we will say that for Z8 multiplicative group, there exists no primitive. I'll repeat once again. Z8 has 4 elements which we have already seen in the previous slide, and we have found this table also. But as we are observing that the order of all these 3 elements, this is 1, for this it is 2, for this it is 2, and this is equal to 2. So the maximum order of the individual element, if you consider, is 2. Whereas the phi n value is coming as 4. So hence we can say that for Z8 there exists no primitive roots. But if suppose we take another example, suppose I take a new example where this is equal to Z7. Alright, Z7, as you can observe that we have 6 such elements which are present. Alright, now this is a tabulation just like a similar case we have done. So this is the tabulation we are looking at. And we are looking at a scenario where the conditions are satisfied with 1 as the remaining. So now we can observe the blocks which are looking at over here. All this is indicative to, and this is the third one actually. So all these are indicative to where the minimum value of I for which the element A 1, 2, 3, 4, 5, 6 has the condition A phi A to the power phi n congruent to 1 mod of n satisfied. So these are the boxes. So what will be the order of 1? So find the order. Suppose I write order of 1 is 1. Order of 2, it's matching over here. See, at I equal to 3, this is equal to 1. Although at I equal to 6 also it's coming. But as we have to consider the minimum value of I, so order of 2 will be 3. Similarly, order of 3, over here it's coming, so it's 6. I'm writing the rest over here. Order of 4, over here, order of 4, so it's 3. Order of 5, 6. And order of 7, oh sorry, 5, sorry, this one only, 6 only. So 1, 2, 3, 4, 5. Order of 6 should be, order of 6 should be 2. Now if you observe, like if I observe over here, that what will phi n? The phi n has been calculated as 6. So here, at least there exists 2 elements, or the order of 2 elements, which matches to the phi n. Hence, we will say 3 and 5 are the 2 primitive roots of the particular set. Am I clear with this? 3 has 6 as the order, 5 has 6 as the order, which matches to the requirement of phi n, which in our case is 6. So, we will say those are the 2 primitive roots for the same places. Okay? That is how we find out the primitive roots. You will soon find that they will have another set of new element also. We'll understand that later. But this is how we consider the order of the element and the primitive roots based on the discrete logarithmic process. Any doubt here? Order of the element and the primitive root calculation? I think I don't have any other. So this is the conclusion, and please make a note of this as well, because this is the easiest way to understand whether or not a group will have primitive or not. This is the condition. Like previous example, we have to make the table, then we are trying to find out. But table we will make only after this condition is satisfied. So the condition is, you can see a set or a group of elements, if you consider G, which is Zn star, and it has a operator, binary operator as cross. has primitive roots only if n is 2, 4, p to the power t or 2 to the power 2 into p to the power t. So this is the condition. So if we can represent this n, this modulo operator, whatever be the number, if we can represent in any of this form, then we can check, at least we can say that yes, this particular group will have a primitive number, primitive root. Now, what are the primitive roots? For that, you need to form the table based on the equation a to the power phi n and all those stuff. And you find out that which particular element has the order equivalent to the phi n which is present. So this condition is very important for that matter. For that only the examples have been given over here. Just you can see 17, 20, 38 and 50. Now if you observe 17, so here my n is equal to 17. Okay. Now if you observe over here, what we are looking at, first comment is it has a primitive roots. We don't know which are the primitive roots. This is just a condition that yes, it is a primitive root. Why? Because it is a prime number, and in a way we can represent that using p to the power like 17 to the power 1. T here is some integral value. Okay, so this p is a prime number. We are representing it all throughout our nomenclature. So this condition is satisfied. The third one, 17 to the power 1. Correct. So we can say that 17 is a prime. Like 17 is a prime and it has primitive roots. It's the same. Z17. Now if you observe the next one, Z20. Now in this case it has more primitive roots. Why? Can you tell me? Why we can say, at least by looking at it, that it doesn't have a primitive roots? Can I represent that by something like a 2 to the power of 20, something with respect to 2 to the power, like for example this one. Suppose it is not a 2, it is not a single 4. Can I have any prime number to the power 1, 2, 3 so that it becomes 20? No. Can it be 2 into some prime number and then that prime number to the power something that makes it 20? It won't be. That is the reason. So the checkpoint is that as 20 doesn't satisfy any of this condition, we can say directly that it doesn't have any primitive roots. Very similar, this analogy is like when we are trying to find out the multiplicative inverse, whether it exists or not. We were checking GCD equal to a comma b is equal to 1 or not. Same thing. It's just a condition to check whether a particular set has a. So if suppose a question comes in, you are given a particular set, you have to find out the primitive roots of the same. First, you have to check using this formula and the logic that whether the set has primitive roots or not. First, conclude that. And after that, you use the formula, the previous slide formula, a to the power phi n, congruent of 1 mod of n, where you find out the table and find out the particular I for which the condition holds true. From there, you find out the maximum value of the order of the element, which matches to the maximum value of phi n. Not maximum value, the phi n value. Correct? Now, you can same observe that 38. So 38 has been represented in this way, 2 into 19. Now this actually forms something like 2 into 19 to the power 1. So it is almost falling this category. Fourth one. 2 into 19 to the power 1. That is possible. So we can say it has primitive roots. Now what are the roots? We have to find out later. That's separate. Similarly 50, it has been divided into this many prime numbers and we can represent easily that at least we can say that Z50 multiplicative group will have a certain amount of primitive roots, what we can calculate later. So what we have observed over this period of time, that primitive roots are important in terms of finding out from a set of elements or a group of elements, and that mostly will be a multiplicative group, from where we are keeping in mind, because this multiplicative group will be useful sometime later, as I can't say DES algorithm and all, data encryption standards and all, they will all consider multiplicative group. That's why it is so important. All right, and the order will change. The magnitude of the modulus will change later on. That's a separate issue. So that is one. So first thing, the order of the group. Then we found out the order of the element. Now we have found out what is the primitive roots. And now we have found out what are the conditions to check whether the primitive roots is present or not. Now last but not the least, these are some of the additional adjoining solution you can say. One is called as this is that if the group has any primitive root, then the number of primitive roots. Now this is the second one. How many number of you have? That will be given as phi of, please make a note of phi of n. So you find the Z10, suppose you have Z10. Suppose, let's take a very simple example as we already know. Suppose it's given, I think, yeah, here it's itself given. So the Z10, this is for with respect to multiplicative group Z10 as a reference we are considering. So for Z10, we know that phi 10 will be equal to 4. We have already derived that. So if it is 10, now 4, and we are already finding out that this is a case where the primitive root exists. So how many primitive roots are present? That will be given as phi of phi 10. So that means we have phi of 4 like this. Like this. Alright, so that is how we are trying to find out the case of the element. So that's why it is coming as 2. Now how we are trying to prove it? You can observe that I think we have taken that example prior itself. Have we taken it? No, I don't think we have taken that. Anyway, it's here itself. So you can see here that it can be found out that the primitive roots are 3 and 7. 1, 3, 5, 7. These were the elements, I think. For Z7, I think, if I'm not wrong. So in that 3 and 7 will be the primitive roots. And if you go on calculating it, you can see the resultant will be 1, which we had already done in the previous case. So we can say from this example that one thing is that given a particular group, we can first identify whether it has a primitive roots or not based on the previous condition over here. Then if it is yes, then we find out the number of primitive roots which are present over there. So based on that we found out that how many number of primitive roots are there. Then you form the table like this and you find out what are the order of the elements which matches to phi n. Am I clear with the whole process involved with this kind of question? You have to first start with this part. You check for the particular group whether it has primitive roots or not. If yes, check for how many primitive roots are present or not. Then follow this table or find out a similar table like this and find out what is the order of individual element and check where the order of the element matches to phi n. So those are the elements which will be considered as a primitive. Also, if you observe here, one of the condition is given over here, which is given as a cyclic group. Okay, this is very similar to cyclic group we already had discussed previously. If G is a primitive root of the group, we can generate the set of Zn, which will also be a part of the group. So you can see over here. So this all element, this calculation, you can see 3, 9, 7, 3 and 1, they all belong to the set Z10 itself. That's just the proof of it. What I mean is, like if G is a primitive root of the group, for example, 3 and 7 is a primitive root. If we follow this process, G to the power 1, so 3 to the power 1, 3 to the power 2, 3 to the power 3, 3 to the power 4, 3 to the power 4. In each of the cases, the final element belongs to the main set itself. So we can say that whoever will be the element, if the primitive root exists within a particular group, the group that it creates is also a part of the main. So that's why they are called as cyclic group for them. Alright, so these are the properties of discrete logarithm and the existence of primitive roots, how to calculate primitive roots and the process involved. Again, you can take any value of n. Even I would request you to actually try out with Z38 or maybe Z50 and check and verify that whether you are able to compute it properly or not. Okay, so because we know that how many number of we can find out what is the phi n for that. Can you quickly find out what is the phi n for Z50? Let's see, because that's already we have done previously. What should be phi 50? How will you divide that? Sorry? Phi of 5 into? Phi of 2 into 5. That is better. 5 of 2 into 5 of 5 square. That may be the case. 5 square can be considered as 5 square minus 5 to the power 1 and 2 can be 2 minus 1, 1. So that is fine. So what will be the value? 20. So the phi n value is coming as 20. So in that case, if that is the case, so phi n is 20. So phi of 20 now you have to calculate to get the number of primitive roots for Z50. Understand? So this you calculate and you later check it that how many roots are there. Now you form the table for Z50 and check that whether it's matching or not. You do it later. Okay? Fine. So this is about the cyclic groups and all. So you can see the primitive roots can be thought as the base of the logarithm. Okay, so what will be the base of the logarithm? For that only the discrete algorithm, discrete logarithm is what we are trying to calculate. So these are the properties you can see. First of all, its element includes all integers from 1 to p minus 1. It always has a primitive root if this is the condition, Zp star, where P is the cyclic group. In fact, you can see this condition is already we have established previous slide. It is cyclic. The elements can be created using g to the power x, which I did. I told you g to the power 1, g to the power 2, up to g to the power phi n. So that we can do. And finally, the last conclusion is the primitive roots can be thought as the base of the logarithm. That's an important conclusion. Because most of the time, what in normal arithmetic we know that the base will be around 10 or maybe e or maybe for binary it will be 2. But now with this discrete logarithm, what we are observing that any base calculation is possible based on the certain degree of calculation. Most of the time we will stick to log 2 only because we will consider 0 and 1 for digital bit. But as this is a generic discussion, the final conclusion is that if we consider the primitive roots, we can find out as that as a base for the set particularly. Right? So this is all about the discrete logarithm part which was there in the syllabus and the necessary calculation. Now let us start off with the last segment that we have. Although this is what we, as you can see the heading and that's there in the syllabus as elliptic curve arithmetic. But ideally, this is applied to a cryptographic system which is given, you can see ECC. But this is not there in our syllabus, unfortunately. So we are not going to discuss about that. But the direct application of this rule or the arithmetic part of it is applicable to elliptic curve cryptography technique, ECC. Now, why we are doing it, you can see the first few lines of it and why we are actually suddenly trying to find out. Elliptical curve arithmetic doesn't have anything to do with ellipse. That's the first thing. It is nothing to do with ellipse. It's just that it follows certain equations which has a cubic expression. Okay? That's the first thing that we learned. Most of the product and standard that use public key cryptography for encryption and digital signature use RSA. Okay, RSA, as I said, like the asymmetric algorithm also. The key length for securing RSA has increased over recent years, and this has put heavier processing load on application using RSA. So by this process of elliptic curve arithmetic, we will try to make sure a smaller set of key, like the number of key elements, key length to be shortened to a certain extent so that it reduces the overall processing, improves the processing speed, reduces the processing load. That's the basic idea why we are doing it. And as you can see, elliptic curve cryptography is showing up as a standardization effort included in IEEE standards. But as I said, ECC will not be taught to you. We will only understand the analytical expression, how we can compute the process of elliptical points for our elliptical curves, how we can generate for a given set of elements. That's what we have to do. Now, as you can see that an elliptical curve is defined by an equation in two variables. We will have a y and we will have an x and we will have certain values of variables which are a, b, certain like that. So we'll see that one by one. Before looking at this, we first look at elliptic curves. You can see here in which variable coefficients are real numbers. This is very simple in fact and interesting to be honest. For elliptical cryptography, an operation over elliptic curves, this is what we are trying to find out actually. That what is elliptical curves? What are the points of a curve? Usually what will be a curve? Suppose I draw a curve like this. How can I draw a curve like this? I need some points, right? I need some points over here. So the technique that I'm going to discuss over right here will give us an indication about these points. what are these points of a given set, which can be given as the optimal curve within which you can choose some certain element for the key generation. Understood? That's the basic objective of it. What I mean is that suppose I form these points using certain rules. So we will bound our search within a particular finite elements, and we will permutate among those elements to find out the keys. So the arithmetic here is to find out those points. Okay, that's where we are heading to. So let's see, we'll start one by one. And one of the important and the advantageous property over here is multiplication is defined by repeated addition. So that means A into K will be represented as K times we will have A addition. So it's only repeated addition that we have to consider. So no subtraction, no multiplication, no division, nothing has to be done. It's just addition that we have to do. So let's see. Elliptic curves, actually, as you can already have told you, elliptic curves are not ellipses by any chance. Nothing to do with this. They are so named because they are described by some cubic equations. And the cubic equation looks something like this. But again, for our purpose, we will reduce that into a much smaller expression. We'll see that in next slide. But this is basically, you can see this is cubic. X is cube. And you can see A, B, C, D are all real numbers. X and Y take values based on the real number. Now, for us, only please make a note of it. For us, it's only required with this equation, y square equal to x cube plus ax plus b. Only this you keep in mind, because that is only relevant for us. So, y square equal to x cube plus ax. What does that mean? That we will go on trying to fix some values on a and b, although there must be some conditions also imposed. Along with that, what we'll have is that based on certain value of x, we will get two different values of y, because it's a y square. So we will get some certain values with respect to plus y and minus y. Alright. So intuitively we can say that there must be some kind of a curve which will be symmetric about y. Okay, so you can see over here, it should be there somewhere. Yeah, last line. Each curve is symmetric about y equal to 0. Let's take an example, then I'll come back here. Let me show you a graph of it, and then I'll explain it. So suppose this is one of the curves that is generated for the equations y cube equal to x cube minus x. So let's take that x cube minus x. So what is my basic equation? X cube plus ax plus b. So here my a is minus 1 and b is equal to 3. So for the given real numbers minus 1 and 0, based on certain values of x, we are getting some graph like this. And if you observe, this is my y, this is my x, and it is symmetric about y. That's being mentioned over there. For any such graph, the property holds true. And an interesting thing that you can observe over here, that for a given value of p, or any value, we will have, like if you consider p value, this is x comma y, and there will be another point minus p which will be represented as x comma minus y. That is what difference. Capital P, x comma y will be some points maybe here. And the same point over here will be considered or represented as minus p. So that will come, one by one it will come, but this is just an explanation of it. So if I go back here, so the basic equation that we have to consider is x cube plus ax plus b, and we have to consider y, which you can observe, y is equal to x cube plus ax plus b. Naturally, the roots will be coming in that way. Another very important point is the second point. Also included in the definition of elliptical curve is a single element O, and it's called as point of infinity or the 0 point. Please make a note of it, because this will hold true for many properties of elliptical curve arithmetic. So O is an element which is basically a 0 point or a point at infinity. It means something like a point where you are converging, something like that. Okay, we'll see that one by one. Right, so this is about the elliptic curves and its some of the property. And you can see this second graph, it has a equals to 1 and b equals to 1. And we are trying to find out the similar kind of graph of it like this. Now, what is the purpose of it? Now, after this we are doing it, we have to somehow come back to that point, that what are these points? What are these points maybe? Like it will be symmetrical. So what are these points? That we have to find out after this. So let's see. Now, if you observe, now consider the set of points E, A, comma, B, which already I explained to you, consisting of all the points X, comma, Y that satisfies the condition using different values of A, B. At this point, we have A equal to, suppose for the first case, A is equal to -1 and B equals to 0. So this is what we have considered. Now you can take any other value, A equal to 1 and B equals to 2 maybe. The equation will change and the nature of the graph will also change. Naturally, quite natural. So that's been mentioned over here. Using a different pair of values of A, comma B, results are different for set of EA. Using the terminology, the two curves in the above figure, the previous one, with this already I have told you that we were having. Okay, so this is just an example. We can have multiple such graphs with respect to different values of A and B. Now comes the last part that we will end up today's discussion with. One is called as the geometric interpretation of addition. As I already told you, for any such elliptical curve arithmetic, we don't have any such option but addition. So you can see it can be shown that a group that can be defined by the set E, A, comma B, that's whatever the element, they should satisfy the condition. Please make a note of this: 4a cube plus 27b square not equal to 0. Now don't ask me why this is considered, because I also don't know why it is considered. But it is a part of what I observed in the book also it's mentioned that it is a part of the geometric interpretation of elliptical curve fitting, something like that. So this is a part of it which we have to consider. It's nothing but a condition. Okay? That what can be the value, what are the values of A and B that can be considered to make the plot possible. So what we have to do is we'll just substitute the values of A and B. For example, in this case, A is equal to -1 and B equals to 0. So if you substitute over here, this is 0, A equals to -1, what will be the value? It's -4. So in that case, it is also not equal to 0. Satisfied. Similarly, for any other value also, you can substitute and you can get the answer. So this is a condition. That condition needs to be made for the particular EAB, this value. To define the group, we must define an operation called addition. You can see only addition, nothing else. And denoted that by plus sign, just like very similar to the binary operation for the group EAB, where A and B must satisfy the condition as given in equation number 2. Okay. If 3 points on an elliptic curve lie on a straight line, their sum will always be O. Okay. So that's what the interpretation is. So let us just stop at this point. Maybe I'll just I'll explain that because this will take a little bit of time. So let us define up to this point. We stop our discussion with where the geometric interpretation of addition with respect to elliptical curve arithmetic has been defined. So what we are observing, what we are trying to focus is that using the arithmetic, we would try to find out the points. This is with respect to general arithmetic we are doing. Now it will be shifted to Galois field, GF field, GF2 to the power n when number is prime. So it will be shifted to Galois field and we will try to find out the existing point. I'll just show you one before we end up. This will look something like this. Finally, we are trying to achieve these points, or maybe another better diagram is there like this. So these are the possible points, and these are the possible set of P which should be calculated using this arithmetic, and later on these points will form as a set to create the P in some other algorithm like RST. And if you are using this algorithm, the key length will be smaller. As the key length will be smaller, the processing speed will be higher and the load will be reduced. That's the purpose of doing all these things. Right? So let us stop at this point. Let us come back next day. Tomorrow we have a class, I guess. So tomorrow we'll finish off with the second module and the rest of the elements what we have.